And this summer I did research in the field of battery prognostic, and my advisor was Dr. Chen. This will be an overview of my presentation. First, I'll define battery prognostics, and then I'll give you some background information about battery prognostics in particular. And then I'll speak on the objectives of battery prognostics and my particular objectives, methods I use to go about accomplishing my objectives, results I get from those methods, a conclusion, future plans, and questions. So what is prognostics? Prognostics is an engineering discipline focused on predicting the point in time when a component will no longer perform some type of function which it's supposed to. And this is basically how the discharge of a battery works. So you start with this initial voltage, which in this case was 4.2 volts, and the battery is discharged until you reach some terminal value of your voltage, at which point the current is cut off. And that's where you see my end of discharge arrows at. And the rate at which this voltage goes from its initial value to this terminal value defines the capacity of the battery. So the primary objectives of battery prognostics include RUL prediction, or remaining useful life prediction. How much longer can a battery be charged and discharged? Predicting the state of charge within a certain discharge cycle. How much longer will that discharge cycle last, basically? And predicting the state of health of a battery, which is basically how the capacity is deteriorating in comparison to its nominal capacity. And my research objectives were to first, my main objective is to predict the remaining useful life of a lithium-ion battery. And a sub-objective of that is to model the effect of rest. Rest is the factor in which I'm determining how it affects the battery and how much longer the battery will last due to the effects of rest. All right. So looking at this plot here, you can see that if a battery is allowed to rest for an extended period of time, then the capacity has a tendency to increase rather than fade, right? As you can see from this right here, this is a plot of the rest. It says length of discharge is wrong. This is a plot of the rest, and this is a plot of the length of discharge. So when the battery rests for a long period of time, the capacity has a tendency to increase, as can be seen by these correlations. So this is my method for finding the effect of rest. First, I take a data set, and from this data set, I record all resting periods, and then I record all time differences between capacities due to these resting periods, and I create distributions for each period of rest to determine what type of effect should it have on the capacity of a battery. So these are the two matrices which I create, which contains all rest periods for the cycle of the lifespan of a battery and all time differences that occur between two consecutive discharges for the cycles within the life of a battery. And this matrix over here, it just contains intervals of time which my rest can fall into. So let's say that my rest lasted for 88,750 seconds, it would fall into this interval. So for each of these intervals, I find all lengths of rest within this matrix which correspond to this interval. And from that, I then find all the corresponding time differences to those periods of rest. And so I take all these time differences and I put them into a vector, and I find the average between these time differences and the standard deviation between these time differences, and I make a normal probability distribution. And I use the peak of this distribution to determine what the effect of a certain length of rest, the effect that a certain length of rest should have on the capacity of the battery. Because the peak of this probability distribution is where the most likely time difference is. And so this is the accuracy of the model that I just explained. The algorithm was trained on data set from NASA Ames Research Center, and it contained 4 different batteries, 5, 6, 7, and 18. The battery was trained on batteries 5 and 6, and it was tested on the first 2. It was trained on to see if it worked at all, and then it was tested on 7 and 18 also to see how accurate it is on data which it hasn't seen before. And in the worst case, it was the percent difference between the predicted value and the actual value was 0.501%, and that's what was when it was tested on battery 18, meaning that the percentage by which the prediction was off was 0.501% of the actual value. And in the worst case, it was off by 100.37 seconds. The worst prediction was off by 100.37 seconds, and that was also when it was tested on battery 18. And so these are just histograms showing the my error. A negative value corresponds to overshoot. I predicted that the value would last, well, that the discharge length would last much longer than what it actually did. And positive value means that I undershot. I predicted that the capacity would be much less than what it actually was. Well, not much less, less than what it actually was. And these are for batteries 5 and batteries 18, and battery 18. And after I've defined a relationship between the length of a certain period of rest and the effect that that period of rest has on the capacity of the battery, a relationship between those two, I want to use that information to predict the remaining useful life of a battery. So the two techniques that I use to predict the remaining useful life of a battery after making this correlation is the good term frequency estimation technique, which basically it takes a sample from a population of phenomenon and it uses this sample to create a probability distribution. And I'll explain a little bit more about that in my next slide. And a particle filter, which basically makes time series predictions based on Bayesian inference. And so, okay, good term frequency estimation. All right, imagine that you're in a rainforest and that you want to know what the probability of seeing a certain animal is. So in order to do this, you take a sample of different animals from this rainforest, right? And in this sample, it's many different types of species within the rainforest, so it's highly improbable that you'll get every single species within your sample. But you want to use the proportions of this sample to estimate the probability of each species, right? But if you don't include the species that you didn't get within your sample, you're saying they have zero probability, which is very inaccurate. And so good term frequency estimation provides a method for not doing that. And so this is how it works. The procedure is you take a sample from a population, and within this population, each species will have a frequency R corresponding to it. And the objective of good term frequency estimation techniques is to estimate R star. Now what R star is the frequency of a particular species which you would have seen if the sample were identically proportional to the population. And so it's calculated by this equation right here. The R star is equal to R plus 1 times the expected value of NR plus 1 over the expected value of NR. Now NR is the number of times that the frequency R occurs within a population, right? But the thing is, we don't know the number of times the frequency R occurs in the population because it depends upon the probability of each species within that population, which is what we're trying to estimate. So the way that good term frequency estimation techniques work is they use the data that you have to make estimations for NR. And really the primary focus of good term frequency estimation techniques is using a heuristic to determine how you go about making inferences of what the expected value of NR should be based on the data that you have. And it's a mathematical procedure for that, which I won't go into because of time, but if you have questions about it, you can ask me about it. And then the presentation or now if you prefer. And this is the role of good term frequency estimation within my RUL prediction. Say that I'll take the rest periods which the battery has already been subject to, and then I'll use the method which I just previously explained to model how the battery should be rested throughout the course of its life by accounting for the rest periods which I've seen within this sample and also rest periods which I haven't seen as of yet. And so every time say that I wait till after 20 cycles to create this probability distribution. After these 20 cycles, for every cycle after that, I have to keep updating my probability distribution because I gain more and more information, therefore I can decrease the uncertainty over time. And this is the role of a particle filter in my RUL prediction. So basically, and I'll explain what a particle filter is a little bit more, but basically just think of a particle as a possible state that the capacity can be in, right? So I generate all these different possible states that the capacity could be in, right? And then I'll propagate the capacities based on the different properties of each capacity. Each capacity will have different properties such as capacity fade, length of rest, etc., right? Which isn't really important right now. But so I propagate these particles with these different properties, and they'll do different things. So what I'll do is, when I propagate them, I'll look at how they were propagated, and then I'll take a measurement of how they were propagated and contrast that to what actually happened. Now, the closer you are to what actually happened, then the heavier the particle will be weighted. And the heavier your weight is, the more probable it is that you'll go through this filtering process, that you'll make it through this filtering process, which is used to estimate the remaining useful life of the battery by modeling the most probable properties of the particle. So, and that's basically what these bullets say. And so after each filtration, I propagate the particles, and that propagation is what's used to predict the remaining useful life of a battery. Now, what are the properties of these particles? The properties of these particles are listed as these parameters. And so the first one is, self-explanatory, it's the capacity. And the second one is a rate of exponential capacity fade. Through experiments, I found that modeling the capacity to fade exponentially, I actually get better predictions than anything else I've tried to implement so far. And so these particles, the capacity fades at an exponential rate. And so the rate at which the curve changes is the rate of that exponential fade. And alpha is just a scalar. It controls the rate at which the curve fades. And beta is your initial capacity. And the capacity can be calculated by using the following equation. And before I use or implement the good turn frequency estimation technique, I want to make sure that I can be more accurate with my predictions if I know the rest which the battery will be subject to, right? You create a baseline. So I'll assume no rest, and then I'll know all the rest. And assuming no rest, I'll make a prediction. Knowing all the rest, I'll make a prediction. And theoretically, I should be more accurate if I know all the rest, right? It's more data. I should be more accurate. So unless I'm modeling incorrectly or there's flaws in my design. So the green dots that you see are me predicting assuming no rest. And these magenta dots that you see are me predicting knowing all rest. And it's obvious that assuming that knowing all the rest, I'm less accurate, much less accurate than assuming no rest. And that's a problem. That's a problem with my design. So that needs to be investigated.
Say that again about your graph. So the magenta one is that you know where the rest periods occur?
Yeah, the magenta
and the quantity of it?
Yeah, I know the quantity, I know the exact time in which it will occur, okay. And I model that in the propagation of the particles.
Okay, so you pretty much are saying that in general, my rested period occurs at this time frame at this quantity almost.
And then I model the effect of it at that particular cycle.
And you're saying, and it seems by your algorithm or whatever that not even worrying about that, you get better results than actually considering.
Yeah, but it's because of the way that I'm modeling the effect of rest. When I model the effect of rest, I say, okay, there's a rest time here, so my capacity should increase by some amount. The amount it increases by, it may not be accurate.
Yeah.
Or there may be other factors which you need to consider it, right? Yeah. And so I'm not modeling that very accurately, and that's causing this high inaccuracy when I'm modeling rest opposed to when I'm not modeling rest. So, all right, while making these baseline implementations to see if higher accuracy could be achieved knowing my rest, as seen in the previous slide, it was much less accurate when I propagated knowing all rest than assuming no rest. And the predictions made knowing rest were off by 40 cycles. Roughly, it's a stochastic prediction, so you can't give exact figures. And then predictions made assuming no rest were off by 7 cycles. So I said that the cycle of the remaining useful life of the battery will be 7 cycles longer than what it actually was, or 7 cycles less than what it actually was. That's the average amount I was off by, the rough average amount that I was off by. So in conclusion, my objective was to predict the remaining useful life of a battery using a particle filtering technique and good turn frequency estimation. And in the process of creating a baseline, I actually discovered that there were problems with my design in modeling the effect of rest. And so that's what needs to be investigated. And my future work will involve considering different designs and different models for the effect of rest and seeing if they're more accurate. And possibly to consider other environmental factors or usage factors which could be detrimental to the capacity of the battery and trying to model those effects as well. Are there any questions?
I'm kind of curious, did you look at any lump circuit models and correspond with your algorithm?
I did look at lump circuit models, but really, to be honest with you, I'm kind of new to the subject.
Yeah, I sort of figured. Yeah.
But I don't think that in predicting the remaining useful life of a battery, I don't think that really would have been that helpful. In this particular case, because the batteries were discharged with direct current, well, the current applied to the load was direct current. And with these lump parameter models, they model the effects of impedance. And impedance really wasn't a factor that was detrimental to the capacity. Well, it is a factor that's detrimental to the capacity of the battery, but it's really it's no viable way to account for that. There's no viable way to calculate that when predicting the remaining useful life of a battery with the data set that I have or in real time.
Yeah.
So.
And also with your background information, because I know like a battery can be modeled as a capacitor with a bunch of resistors, which then would make you conclude that it makes sense that it'd be exponential because of that fact, because of how, right, how a capacitor discharges and charges. So I mean, just with your I think you did well compared to what your knowledge is. So, just to throw that out there.